Good afternoon. Welcome to lecture 103 and 104 on thermodynamics of materials. Today we will discuss Gibbs-Duhem equation. Actually we will resume solution thermodynamics and we will pick up Gibbs-Duhem equation. I started in the last class. This first line I started, then some discussion about the first line. The first line is very important. If you can write the first line correctly, then no problem. Then you can move on. Okay, using your rules of differential calculus or differentiation principle, you can go ahead and use the thermodynamic concepts. You will get to the final equation. Let us see. Before actually, I have to little bit some clarity. This is dependent. This is left hand side is dependent variable. This is independent variables. Variables here this side, and what else? This is a system, multi-component system. Multi-component system, and so our solution 1, 2, 3. So it can be 1, 2, 3, 4. Okay, four member of a 4 component, 5 component system. So start. So the starting line is G prime. The extensively written G prime. G prime is a function of this. Okay, extensive property. So now I have to remove these lines. Okay, these are all discussed. As I told you last day that I will start directly from this point. Okay, so function of. So this is, so let me remove this. Just clean up this part so that we can get enough space to write the subsequent lines, and okay. So today we will first consider Gibbs-Duhem equation, and later on, subsequently, once we have derived this Gibbs-Duhem equations, then we will consider integration of Gibbs-Duhem equation. So this will complete today. So start. So if it is this one, solution thermodynamics. Okay, this is equation, Gibbs-Duhem equation. Gibbs-Duhem equation. So let it rest for a while. Start. This is starting line, or dg prime is what? Del g prime, as you know, del p at constant temperature N1, N2, N2, N3 times dP plus del G prime by del T at constant pressure N1, N2, N3 times dt plus del G prime del N1, okay, sequentially here temperature pressure both constant and N2 N3 are constant times dN1 plus del G prime del N2 constant temperature pressure N1 N3 the remaining two constant times dN2 and the last one del G prime over del N3 under constant temperature pressure and N1 N2 times dN3. This is this. Okay. Now, what is this? This is actually, I tell you what is this? Del G by del P under constant temperature. Recall, and always you have used the dG is VdP minus SdT, from which you get what is V? Del G del P under constant temperature. And S is minus del G del T under constant pressure. Remember, this is for fixed mass, fixed composition. Okay, fixed composition. So actually, if it is a fixed mass, fixed composition, you have to write here fixed mass, fixed composition. Here you see they are already there. N1, N2, N3 fixed means it is a fixed mass and so fixed composition. N1, N2, 3 fixed. So it is actually following this. So what will be del G prime by del P? Nothing but V. But since it is extensive, so you have to write extensively what this should be V prime, extensive to extensive. Likewise, what is this? This will be likewise, again fixed composition, fixed mass is given arrow to minus S prime. And you know these are actually well known to you. It is the partial molar free energy definition, basic definition of this. Partial molar free energy G1 bar, and this is partial molar free energy up to G2 bar, and this is G3 bar. Okay, so what you have now under constant pressure and temperature. So I write constant pressure and temperature. Constant pressure and temperature, what you get? What you get is this. Since it is constant pressure, so dP is 0. So first term will be 0. Plus second term likewise constant temperature is 0. Plus you write this G1 bar dN1 plus G2 bar dN2 plus G3 bar dN3, or you can write here dG prime PT is G prime G1 prime dN1 plus G2 prime dN2 plus G3 prime dn3. You may recall that G1 bar is partial molar free energy of 1, and these are for 2 and 3. This partial molar free energy is also known as chemical potential. Anyway, so label this, the first line. This will be actually a form of Gibbs-Duhem, but I will actually uh, uh, define them, or so I will name them at the end of this. Okay, summarize them. This okay. Collectively, I will give them. So next is what? This is one. Okay. Now at a given, just wait a bit. Also, at a given pressure and temperature, so what is, we know G prime is what? G prime, total free energy of the system. Recall last time this we did number of times, N1 G1 bar. This is not as this is written as a function, but this is I am giving at a given pressure and temperature. What is G prime of the system? It is the total free energy contributed by the components of the system. Total free energy. So what is the contribution of one component, one G1 bar per mole, and how many moles are there? N1. So total contribution of one is N1 G1 bar. This I discussed previously. N2 G2 bar plus N3 G3 bar. Okay. So at a given pressure and temperature, we actually, or I am taking the differentiation, differential under, since it is under pressure temperature. Actually, by the way, why I have said pressure, given pressure and temperature? Because this G1 bar is a function of pressure and temperature. At a given pressure and temperature, that we have actually put the system, okay, in, that is you have exposed the system, you have put the system under certain pressure and certain temperature. Under those conditions, given conditions, G prime is nothing but the G1 bar, etc. What is the, then you might ask, sir, what is the role of pressure and temperature on N1? No, nothing. Number of moles have nothing to do with pressure and temperature. G1 bar. G1 bar is a function of pressure and temperature. Hence, at a given pressure and temperature, similarly G2 bar and G3 bar. So dg prime pt was obviously we will write is what? This completely differentiate this. N1 dg1 bar plus N2 dg2 bar plus N3 dg3 bar. This is one part as it. Then take the other one, G1 bar, and now consider n as the variables. N's are the variables. Here, these are the variables. So G1 bar dN1 plus G2 bar dN2 plus G3 bar dN3. Call it equation 2. Now from 1 and 2, compare 1 and 2. What we get? See, left hand side same, so right hand side must be same. That means these are there. So these terms, these terms together is 0. So from 1 and 2 we get N1. Okay, sorry, I said that this is not the Gibbs-Duhem equation. Gibbs-Duhem equation will come just now. Okay, is what? This is actually this, we obtained this relation from this, starting from this. So I'll give you Gibbs-Duhem soon. So N1 dg1 bar plus N2 dg2 bar plus N3 dg3 bar is 0. This is your Gibbs-Duhem equation, but I will list at the end. So just give this equation a name. 3. Equation 3. Okay, N1 dg1 by. Okay. Now dividing through by sorry, dividing through by n1 plus n2 plus n3. What you get? N1 divided by n1 plus n2 plus n3. Total number of moles. N1 divided by total number of moles is the mole fraction of 1. Is x1 dg1 bar plus x2 dg2 bar plus x3 dg3 bar is 0. This is equation 4. This is equation 4. Okay. Noting dgi bar is what? Recall RT D ln AI, activity I. So substitute this here, or x1 RT D ln AI plus x2 RT D ln AI. I'm sorry. It is A1. X1 A1. First one. Second x2 is A2 plus x3 R3 ln R3 D ln activity 3 is 0. They together is 0. Or if you cancel RT, or you get this relation x1 D ln A1 plus x2 D ln A2 plus x3 D ln A3 is 0. So this is another form of is called 5. So these are 3, 4, 5 are Gibbs-Duhem equation. I will actually give you at the end. Okay. Now actually we actually want to, from this I want to remove these are already over. Remove this. Remove this. Because so what is this? Now if we actually reduce the number of components, well, okay. For the two component system, for the binary system AB now, for the binary system AB, for the binary system AB, the binary system AB, we can write so this one we can write what? Tell me what we can write. X1 or say not 1, say call it A now, AB, not 1, 2, 3, but AB, not 1, 2, 3, but just two component 1, 2 or AB, X A DLN activity of A plus XB DLN activity of B is 0. We actually write this because for binary system, because we will often deal with binary system, and moreover this is simple. So okay, at least a simpler system we should be able to work with and handle. Then we can take up the 3 component, 4 component, 5 component. So often we will actually, in fact, we often will consider binary system problem based on binary system. So binary, if we can understand binary system and we can handle binary system well, then we can venture to take up the ternary systems. But anyway, these relations are all given. Relations are given. So you can actually add on for the 4th component and 5th component like this. Okay, 4, 5, 6, etc. But anyway, let us reduce the number of components to 2, and this is AB system. This is this. This is okay. From this we get this. So this call this. Then you give a box. Call it 6. Equation 6. Then now okay, very well. 6. Acha. Also, okay. Also, we know. X in a binary system, right? Once more, right? In a binary system, AB. System means solution. System means solution. So iron manganese solution. Okay. Or iron carbon solution. So in a binary system AB, what we know? XA mole fraction total as 1, XA plus XP1, or DXA plus DXP is what? 0. Okay. So this is okay, equation 1. This we don't know. This we can remove also. These are preparatory to Gibbs-Duhem. This equation 1 is preparatory to Gibbs-Duhem's. Okay, kindly. Next, XA plus XB is 0, or XA DXA over XA plus XB DXB over XB is 0. Or I'm actually saving line, or yes, or let me write here, or XA, what is DXA by XA? TX by X is D ln X, or XA D ln XA plus XB D ln XB is 0. Call it which equation? 7. This is very simple. Looks like this, but simple. Now, dividing by 6 divided by 7. Dividing 6 by 7, we get what? You just see, you divide, you get X. Divide means, okay, sorry. 6 minus 7, I am very sorry. 6 minus 7. So X a common first term, X a common D ln A minus means divided by log, divided by X a log, minus means log divided by plus XP d ln ab over xp not, okay, or is 0, okay. So in fact this actually gradually remove this also, this line, or x a d ln, what is this, a divided by x a is gamma a, activity coefficient is gamma a, plus xp d ln gamma b is 0, and of course you will highlight this and label this equation 8. So I tell you what, so this at the end it is 0. This and these three are Gibbs-Duhem equations, different forms of Gibbs-Duhem equation, and different forms. Okay, it is in terms of partial molar free energy. This is in terms of mole fraction and partial molar free energy. This is in terms of moles and partial molar free energy. This is more often used. This is in terms of activity. Gibbs-Duhem equation 1, 2, 3 for ternary system, and these two, this is up to 5, 6 and what is 7? Okay, no, this is 7. Okay, 6 and 8. 6 and 8 are again Gibbs-Duhem equation for binary system. One in terms of activity, another in terms of activity coefficient. So let us note down this point so that we have no difficulty to follow. Equations, tell me 3, 4 and 5. Equations 3, 4 and 5 are different forms of Gibbs-Duhem equation for the ternary solution, 1, 2, 3, and what else, 6 and 8. 6 and 8, not 7. 7 is not. 6 and 8, and equations 6 and 8 are the Gibbs-Duhem equations, equations in terms of what, 6 and 8, in terms of activity and activity coefficient, in terms of activity AI and activity coefficient which is gamma I, respectively for the binary solution AB, for the binary solution A, B. That's it. That's it actually. With this, we have completed this Gibbs-Duhem equation derivations. We have derived ourselves as if these are this. Okay. So one thing quickly follow. What is the significance of this line? Say, for example, or this line, or this line, or this line, etc., etc. Okay, or this line. If follow, it means if this term increases, the other second term decreases, so that sum remains 0. They together is 0. If one term increases, the other term must decrease. Let us see. Let us see if it is easy to follow. Why? If mole fraction increases, XA increases. You know what is the consequence in a binary system? Binary system is simpler to understand. If XA increases, you know two things you can say easily. That activity of A will increase. As mole fraction increases, activity increases. And at the same time, you can say that mole fraction B decreases. XA increases, XB decreases because they sum to 1. XA plus XB is 1. They together is 1. So you see, when this increases, this term increases, and then this term decreases, and if XB decreases, then AB activity also decreases. So this term increases, that term decreases. This is the significance. So that this increase decrease just nullify each other and making it 0. Result is 0 always. This you can apply everywhere. Everywhere. I am showing you here also. If you increase the number of moles of one, it is I am showing here also. Here, second one, binary. Then also similarly, if you increase the XA, okay, you will see gamma activity, mole fraction if increases in a binary system, if mole fraction increases, gamma A, suppose you consider actually, okay, gamma A increases. Gamma A will increase when X is increasing. Gamma A, actually I should tell you, gamma A should decrease if it is positive deviation. If it is negative deviation, it will increase. So by the way, so X increases, say suppose negative deviation, say X increases, gamma increases. Okay, gamma is less than 1 as it is increasing, so it becomes 1 finally, increasing. So X increases, gamma increases, and when X increases, XB decreases. So gamma B also. Okay, XA increases, gamma A increases, as I said. So negative deviation here also. So this also XB decreases, gamma B decreases. So again, so this term, whole term increases, this term increases, this term decreases. Similarly, you can apply here. Say partial molar free energy is a function of composition. If x1 increases, g1 bar increases. If x1 increases, g1 bar increases. So the g1 means okay increasing. So if this term increases, then these two together will have what will happen? If x1 increases, x2 decreases. No one can stop. If it is a 3-component system, if x1 increases, one mole fraction increases, other two, sum is 1. So they must be reduced. So that total is 1, remains 1. So x2 decreases, x3 decreases. And when these decreases, then these are also, this partial molar free energy is function of composition, these are also, these also decrease. So when this term increases, these two terms decrease, so that the total remains 0. So this is the significance. So very easy to follow that what is happening. So this, and here also again activity. So same problem, same thing. Okay. So so we have actually kind of completed. So we can draw a line here. It is Gibbs-Duhem equation is this means derivation is over. So let us move on to the Gibbs-Duhem equation. Gibbs integration of. Next topic is integration. Let me remove this. I have to say, do you want to remember? Okay, you want to keep it for a while? Okay, I'll write somewhere. This one. In case you forget, I'm writing at the once underneath X this one. D ln A plus XB D ln AB is 0. AB is 0. Just I am saving this, okay, because for reference, okay, this, just save this, okay, otherwise I will remove all these things, okay. Okay, okay, fine. So remove this, remove this. All this part is, initial part is over. Next part will be integration. So, okay, now we will consider the integration of the Gibbs-Duhem equation. So, just remove this right face. This is actually this integration of the Gibbs-Duhem equation of the Gibbs-Duhem equation for a binary system AB, for a binary system AB. So this is the next topic related to Gibbs-Duhem equation. Okay. So objective. What is the objective of this? To find the activity. To find the activity of a component of a component a component A A at a given composition of the solution at a given composition of the solution composition of the solution. What is the name of the solution? Is AB when the activity of the other component. Who is the other component? Tell me. B. When the activity of the other component B is known as a function of composition. Is known as a function of composition. This is the objective. That means I know the activity versus composition relationship for the component B. For different composition, different activities for B. Using this data, I can determine the activity of A at any composition. At a given composition means at any given composition we can determine. Means for this we don't have to carry out any experiment. We will carry out experiments for the component B, suppose, as a function of composition. Then for A we don't have to. If we use the integration of Gibbs-Duhem equation, we can find. So, in a way, thermodynamics saves our time and saves our difficulty saves our effort, helps us, okay, reduce our time, and okay, saves our time and saves our effort, as I said. Okay, good. So the relevant start. The relevant the relevant the relevant Gibbs-Duhem equation to start with. Relevant Gibbs-Duhem equation is, since it is about activity, so pick up the is x d ln a plus xp d ln ab is 0. This is the starting point. Then what we'll do, or you write here, or just instead of using ln log base e, we use log base 10, means log. So x d log activity of a plus xb d log activity of b is 0. Okay, this is fine. Or just continue. Or d log a is what? Or d log activity of a is what? Tell me. Minus xb over xa d log ab activity b. Okay. Now if you integrate this, integration gives to him integration or d log. Remember, we have to find activity of a left hand side at a given composition. So d, first you actually formulate the relation, then you apply it. Okay, with data. So d log a is integrate is what? I should write this way: xp by xa, little bit of manipulation, d minus log ab, no problem, integration. Now about integration, we should use lower limit is such composition for which activity is known universally. What is that composition? A, we don't have any origin. This is already known. What is that? Xa is 1. This is the lower limit. Because for this activity is 1. Pure A. And what is this one? Xa is the composition for which you want to determine the activity of A. At the activity to find at a given composition, this is the given composition. Xa is Xa, maybe 0.3, 0.4, 0.5, etc. We take example. Xa is Xa. Well, this one would be what? Xa is 1. And if Xa is 1, but since it is about B in terms of d log AB, etc., etc., so write also what is the meaning of this? Xb is what? 0. Xa plus Xb is 1, recall. And what is this? When Xa is Xa, this means in terms of Xb, that is Xb is Xb. This is the upper limit. This is the lower limit. Okay. Sorry, Xb by Xa. Xb by Xa. Okay. Okay, very good. Call this equation that is xb is 0. Or you also write here that is, better write that is xb is xp. Xp is xp. Okay. Xb is what? 1 minus xa, and 1 minus xa is xb. So xb is xp. Very good, very good. Next, let us call it equation 1. we will use this equation to determine activity of A. Okay. So suppose the following, giving that activity versus composition data for B, the other component, that must be given. Otherwise, you have to carry out experiment. This is without doing experiment, you are getting activity of A. Very interesting. This is a blessing of thermodynamics, particularly here in the form of Gibbs-Duhem equation. We don't have to carry out experiment, which are very, we may be difficult to determine activity. But anyway, suppose the following AB versus XB data are known. Experimentally found, you can typically consider this data. I'm making a table, kind of table, AB, then XB, then for some reason XB, for why? The reason is very clear, XB by XA. This one, I'll explain. First is data is XB is 0, is 1, when then 0.1, then 0.2, 0.3, 0.4, 0.5, and we don't have enough data. So 1, last one. So what is the corresponding AB experimental found for 0 when XB is 0 in a binary system? AB is obviously don't have to carry out any experiment, 0. 0.1 suppose gives it 0.2. 0.2 activity comes 0.2, means you know what is the gamma. Gamma is 2, means positive deviation system I am discussing very clearly here. Okay, when it is as it is increasing, this activity coefficient gradually decreases to 1. So 0.2, next one is 1.6 perhaps. So it is actually 0.16, 0.1, 0.2, 0.2, 0.36. Okay, I'm very sorry, not so much. So here activity coefficient is 2, here activity coefficient is 1.8. So very good, as increases. So positive deviation gradually activity coefficient decreases to finally 1, merges with the 1. Anyway, 0.3 is what? Let us, without wasting time, 0.3 is 0.45, 0.3 is 0.45, 0.4 is 0.48, and 0.5 is 0.55. And what is this? XB is 1. When XB is pure, activity of B is no experiment required. So these two terminal data are not required, any experimentally not required. Okay, they are known. Okay, so XB by XA, you do this. What is XB by XA? Because this will be required here. This will be required. XB by XA is what? What is when XB is 0? What is XA? 1. When XB is 0, XA is 1. So 0 by 1 is 0. When it is 0.1, XB is 0.1, XA is 0.9. 0.1 by 0.9, 1 by 9 is 0.11. 0.2 by 0.8, 1/4, 0.25. 0.3 by 0.7 means 43. 0.4 by 0.6, 2/3, 0.67. 0.5 by 0.5 is what? 1. When it is 1, XA is 0. XB by XA is what? 1 by 0 is infinity. Okay. Let me check, is 0.125, 0.43, 0.67 is okay. It's very good. See right here, since XA plus XB is 1. Happy? I am removing this because this relation is written here. This relation is written here. So I am removing this, not required. We don't have to save anymore. This is already there. Now next is main task. Now following equation 1 following equation 1 let us plot xp by xa versus against what x by xa, where is this aj, y dx, y y y dx, plot y versus x, area under the curve will give the integration, y dx integration between limits, area under the curve between two limits. So this will be the approach, xp by xa against minus log ab, minus log ab using the above table, using the above table. Table means this is the table, this is the table, this is the table. Okay, above table, above table. Okay, very good. So so now what you'll get, the resulting plot is a curve, is a curve is a curve as given in figure, as given in figure 1. So this is the time to draw the figure. Okay, let us concentrate on this drawing. It is better I draw here. Here I should draw. Yes, I should draw here. Let me try once more. Once more. Okay, this is xp by xa. This goes to infinity, plus infinity, and this is minus log ab. This goes to again plus infinity, and this is your 0 0. Okay, this is your 0 0. Okay, now you see one thing. One thing you see. Acha, this is 0. I'll show you. This is it will not be scale. Okay, not to scale. This diagram will not be uh, in scale. Okay, not to scale. Okay. So let me draw first this. First of all, say when xb by xa is 0, when this value is 0, what is this value? When it is 0, what is the log ab? When this is 0, what is the log ab? Log 0 is minus infinity, and minus minus plus infinity. So plus infinity. So when it is 0, this is plus infinity. And similarly, when minus log ab is 0, when minus log ab is 0, what is the meaning of this? Log ab is 0. Means ab is 1. ab is 1 where? Here. Here. What is the xb by xa? Infinity. Okay. We write a plus infinity, maybe plus infinity. Repeat. Next one, this one. When minus log AB is 0, what is the value of xb by xp over xa? When minus log AB is 0, what it means? Activity of B is 1. What is that point? This point, this column. And what is the xp by xa? Is infinity. So infinity. So when this is 0, this goes to infinity. When this is 0, this goes to infinity. So it will be asymptotic on either ends. So let me draw this. Sorry. Not good. This will intersect, asymptotic. It goes to infinity. So now, suppose this is, now I scale this. When xp by x1 is 1 here, okay, xp by x is 1, I am giving this value. This is the scale. Suppose this is 1. Suppose this is 1. Then this will be what? Tell me. The 0.5. Very good. 1.5. I will call this 0.67. 0.67, 0.5, 1.67, okay? Because we are only up to 1. xp by x is up to 1, then infinity. Then it is infinity. No other data is, we are not using, okay? There may be more data, that is better. But we are using with this data to give a demonstration how Gibbs-Duhem integration can be done, okay? So first, 3 points, 0.61, 0.67, 0.5, 0.5, 0.43. Acha, 0.5, it is maybe, don't know, this is the 0.5 cell. 0.43, then 0.25. 0.25 will be between 0 and in the middle, about middle, 0.25, and then it is 0.11. 0.11. Now put the values. This is the scale I have used, okay? Okay. Not uniform spacing, but you have to accept this. Okay, try to understand how it should be done. Okay, then you later on you will actually use proper scale and appropriate scale, and okay, division should be okay and proportional. So 1, what is the value of 1? What is the xp by xa is 1? What is the AB? AB is 0.55. What is the log AB? Log 0.55, and minus log AB is log minus 0.55. So I am showing you. What is this value? You give this value is what? Minus log 0.55. This is, so I am showing here, minus log 0.55. This point. Minus log 0.55, 1 is where? 1 and here 0.55. So log of that is log 0.55 and minus log AB. So minus log 0.55. Next is 0.67. I am writing since this place is the 0.67. Tell me what is this? AB 0.48. 0.48 and log 0.48 and minus log AB is minus log 0.48. This one. Second one. Third one is 0.5. I am using 0.5 is actually 0.5 xb by xa 0.5c. It is not there. This is actually I'm using red for some reason. I'll explain. This is in red. 0.5. This will be the unknown given composition for which this will be this. About this, I'll explain. Xb is 0.55, how it can be possible. So this is the unknown composition, or this is the, I'm very sorry, this is the composition for which the activity is to be found. So 0.55, I draw this point. Achha, by the way, you do one thing. You give a circle here. You have this data, circle, circle. This is also, this is unknown. These are don't do this. Okay, known one should do first. Known one. Okay, very sorry. Okay, so next is 0.43, 0.67, 0.43. What is this value? 0.45. So 0.45, 0.5, 0.45. What is this value? 0.43 minus log, sorry, minus log. Achha, this minus log A is the scale I am writing here. Minus log AB is plotted. Okay, you just write this. Okay, this side. So it is minus log what? I'm sorry, this was log minus log 0.48. 0.48. 48. 48. Okay, good. Minus log 0.48 from here, minus log AB. Then next one is what? 0.43 minus log 0.45 minus log 0.45 minus log. Okay, so 3 points I have already. The next point is 0.25. 0.25. So give this is a point. This is a data point. Data point. These are data, experimental data. Data point. This is another data point. This is another data point. Okay, good. Next is this one coming. 0.255. 0.255 corresponding to 0.36. So this gives you, this is very easy to write, minus log, actually right here, 0.36 underneath, minus log 0.3, you understand this. And last one is, I give a point here, data point, data point. Good, good. You understand, 1, 2, 3, 4. 1, 2, 3, 4, so far. The last one is 0.11. 0.11 is what? This point, this one. So draw this corresponding value. Sorry. Here, the data point. What is this? Log minus log 0.2 minus log, at least if I write here 0.2 just nicely, okay, beside log. Okay, so these are the data we have. The question next is, these data I have plotted, and this graph, this is what actually you see. Okay, now let us take, suppose we have to find, suppose next, suppose we are to find, we are to find what we have to find, the activity of A. Always follow this, always follow this. The activity of A, which is nothing but A, okay, activity of A for the composition of the alloy, for the composition of the alloy for the composition of the alloy or solution. Alloy or solution, same thing, interchangeably used. Solution, which composition I am giving you. XA is for which composition? XA activity must be measured against a composition. It varies with composition. So, a given composition, XA composition is what? XA is 2/3. I am writing 2/3 because you know it is actually is 0.666. Okay, and XB is obviously XB is 1/3. If XA is 2/3, XB is 1/3. 1/3, that is 0.33, sorry, 0.333. Happy? Giving XB by XA is what? XB by XA is what? Tell me. XB is 2/3, XA is 2/3, XB is 1/3. So 1/3 by 2/3, half is 0.5. X is 0.5. So from equation 1, so we can write this. From equation 1, now, okay, recall this. From equation 1, you use this. What you will write this? From equation 1, you use this now actual value d, right? D log A integration d log A is what? You write, see here, integration xp by xa, you know, xp by xa, okay? xp by xa d, oh, minus log, yeah, okay, see, d minus log ab, okay? So xp by xa, these are. What is the limits? Actually, I gave you here, xa is 1. What is xa is xa? Now, what is this value? You know now what is the value? xa is 0.666, this composition. 0.666. Similarly, you do this here, xa is 1 means what? What is the meaning of xa is 1? Xb is 0, right? With this side dealing with b, xb is 0, but here you have to give xb by xa in terms of xb by xa. What is the xb by xa corresponding? Is 0 also. Xb is 0, xb by xa is 0. How much time? 1 or 9 minutes. Okay, that time. XB is this, and then goes to what? What here? XB is what? XB is 0 to XB is 0.33. 0.33. But what is the XB by XA is what? You write. What is the meaning of this? XB by XA is what? I don't have space. I should write right here. XB by XA is 0.5. You understand this? This is XB. Oh, here also. I am very sorry. X is 0.66. It's okay. This side is okay. This side I have XB by XA. Okay. What is this? What is this? What is this? D minus log D D. Okay. XB is 0.33. What is the meaning of this? XP by, what is the meaning of this? XP by XA is 0.5. So we have to integrate between xp by xa is 0 here to 0.5. And now 0.5, for 0.5, you say this 0.43, 0.6, we have to read of this curve. First of all, you get this experimental curve and join, and this side is infinity, that side is infinity. So 1, 2, 3, 4, 5, 6, 7, etc. So just draw a curve, smooth curve. Then from this, corresponding to this xp by xa is 0.5, you read of this graph what is the value of x-axis minus log ab. If you do this, I tell you what. See, supposing it should be somewhere between 0.45 minus log 0.48 and minus log 0.45. So I am actually taking it. I have considered it minus little below further to identify or to, okay, to actually with this um, to identify this point actually to log what value minus log what value, it should be between 0.45 0.48 minus log. So let us consider it is minus 0.46 minus log 0.46. Red, about this given composition and unknown activity of A, I have used the red color. In the red I have shown 0.5 is the composition. Composition means xb by xa. xb is 0.33, xa is 0.66. xb by xa is 0.5. Corresponding value I have considered log minus 0.5. I say I am writing say. It will be somewhere between this, but let us consider this. This will not affect much. Okay. So good. So what is this now? So at this point actually I actually give this. I give a star here. I give a star here, and I am using this objective. Since you know the objective, I am removing this. The related Gibbs-Duhem equations also, these are all over. So I am writing from this point. What we'll do next is okay. So if you do this integration or log a do the integration d log a at what value? Upper limit at xa is 0.666 minus lower limit xa is 1. Okay, from this. Okay, very good. This left hand side is okay. Right hand side. Oh, here actually I made a mistake. The integration sign is this integration sign. Okay, xb is 0, etc. Integration sign. So what is this? I am writing this again. Is area C y dx area under the curve obtained by plotting xb by xa against minus log ab. So area under the curve like p dv area under the curve integration y dx area under the curve. Okay, so this is also so area under the curve between which point and which point? See which point and which point? You tell me. Between, follow this. xb by xa is 0. xb by xa is 0 to xb by xa is 0.5. From 0 to 0.5 and corresponding this one. So 0 means infinity. 0.5 means corresponding log ab minus log ab is this point. So this part. I'll show you. Area under the curve. Sorry. Between Go step by step. Between, is it follow? Limits between xb by xa, xb by xa is 0 and xp by xa is what? Tell me. Xp by xa is what? 0.5. 0.5. The corresponding the corresponding the corresponding write this. The corresponding minus log AB is what? Tell me. Minus log AB. Oh, sorry. Minus log AB. Do one by one. When xp by xa is 0, what is the minus log AB? Infinity. Is right here, since plus infinity may be better. Infinity. Plus infinity. And what is for this one? The lower limit is infinite and upper limit 0.5. 0.5. What is the value here? Minus log 0.46. Okay, minus log AB is what? Minus log AB is what? Corresponding to xb by xa is 0.5. Red. What is the minus log AB? Is minus log 0.46. Minus log 0.46. Is minus log 0.46, which is log fraction, log decimal is equal, log decimal will be negative and negative positive. So what it will be? A positive fractional quantity. A positive, right. A positive fractional quantity. Fractional quantity. And it is actually redundant to write that it is less than plus infinity. So log fraction and also positive fraction, but no doubt, no question, it is less than plus infinity. The reason is plus infinity. Okay. Hence, the minus log AB, see, log AB decreasing, minus log AB decreases. This line I am removing. This line. These are all used already. Minus log AB is decreasing. I tell you what, I'll give you answer. I'll show you. The area under the curve will be negative. But why it is negative, I will explain. Answer I will give you. And what is the area under the curve? Which area? The area enclosed between these 2 points. Okay, this point and this point, infinite. Or corresponding to this point and this point corresponding to this, and this is this. So this will be confined between this point and this point. This line and here. And that will be negative. Explanation is coming here. Hence the minus log AB is decreasing as xp by xa, as xp by xa is increasing, moves from 0 to 0.5. See here. xv by xa moves from 0 to 0.5, and what is this, gentlemen? When it is 0, it is plus infinity. When it is 0.5, it is minus log 0.46, means a fraction, positive fraction. So it is decreasing from infinity to this value, decreasing this minus log a2, x-axis. While y-axis is moving from what value? 0 value, 0 value to 0.5. 0 value to 0 value to 0.5 means here to here. So this is actually let me write is noting that 0 to 0.5, noting that noting that noting that what is noting not, noting that xb by xa is positive, xp divided by xa is positive, we have seen it is all positive. 0 is here, positive, positive. Xb by xa positive. The area under the curve, area under the curve, area under the curve is negative, is negative. This is the explanation, but I will give you a simple example to make you understand this. So so it is negative, or or what is this value? This is equation. This is the equation. Area under the curve, which is negative, I have said only. What what is this? What is this value? This value is what? When x is 1, activity of A is what? Pure substance 1. Log of 1 is 0. So we get only this. Log A at xa is 0.666. So this is our desired goal, to find the activity of A, given activity composition relationship for B at a certain chosen composition or any composition. Xa is 0.666. This we have chosen only, any composition. So this is what? So this is nothing but right here is right is area under the curve, area under the curve, area under the curve given by the shaded part. Shaded part given by the shaded part is a negative quantity. As is negative, I have said, is a negative quantity. Negative quantity is a negative quantity. Okay, very good. Before I take up, okay, from here, I actually explain you why it is negative. Easy example. Suppose you are plotting illustration, simple. So write this simple illustration. This side, this segment. You use this simple illustration. Illustration of positive area under the curve, of positive area under the curve, and negative area under the curve. So why I am showing this. Just the example. This is y is 0 here. This is x is 0 here, y positive, x positive. Now this is the equation of the curve y versus x relation, straight line. Now if I ask you what is integration y dx between x is x1 and x is x2, what is this? Positive, negative, etc. What is x1? Say this is x1, that is x2, x2, x-axis. What is this area? Area is given by this shaded part. I will give the shaded part. I give the shaded part here. But I'm with the examples, you will be more convincing and convinced, and you will be appreciate. This is the shaded part. This is area under the curve. This is area under the curve. Is what? Area under the curve. Y dx I have written here. Okay, positive is what it is. Acha is positive. Area under the curve, shaded part. I have given here. Area under the curve, negative area under the shaded part. Okay. Part is what? From x is x1 to x2. What happens here? Why it is positive? Follow. Because y dx, y is positive or negative? Check first. Y is positive. From this, y is positive segment. What is the negative y? This side, if this is curve is here, y is negative. Or here, continuously here, y is negative. Below this, it is 0. So negative below this. Below this, it will y would be negative. Below this line, y will be negative. So, but it is positive. Y positive, and now check if dx is increasing. X is increasing. Here x is increasing. X1 to x2. X2 greater than x1. So since x is increasing, y positive, x increasing means result is positive. And on the other hand, so if I have to write anything, why positive? Why? Question is why. Let me write the answer as I have said already. Since because two factors to say y is positive and x increased from x1 to x2 and x increased from x1 to x2. These two factors makes y positive. Okay, and if you check this, okay. In contrast, if I ask you integration of y dx again, but not x is x1 here. Here x is x2, and here x is x1. x2 to x1, x2 x decreasing is what will be the area under the curve? x1, x2 is x1 is what? Negative. The same area but negative value. Why? What is the reason? Again, because I am writing why. Achha, I am writing here. I can give a star, this double star. Yeah, this part. It will over here. Double star. Why? Why? Because because y is positive, because y is positive still. Y is positive still. Y is positive, but But what you have written? But x decreased from it has x1 to x2 increase, decrease from x2 to x2 to x1. It is decreasing. So dx actually then be negative, and positive negative means negative. So the multiplication is negative. So this is why this is negative, this is positive. So now apply this concept here. Here you see x, y. Pretend this is what is this? This is y. X, pretend xp by x is y. Dx, this is the x. This is the x minus log ab. Now you see x b by x y is positive. See, between these points, between these 2 points, I have said shaded area. No? Shaded area, I am giving the shaded area. How shall I give you the shaded area? I can give the shaded area with red will be better. Red will be better. Area another cup full. This is the answer. This is negative. Why? The same reason x b by x is positive. But what happens to this gentleman? Minus log of x. X is decreasing from, you see, here I wrote somewhere, x as this moves from 0 to 0 to 0.5, x by x, it moves from minus log of decreasing. Decreasing from where? As a decreasing from infinity to minus log 0.46. Follow. X by x is 0 corresponding to this lower limit. So this is starting from here, plus infinity. Minus log f is starting from infinity. And when it is xb is 0.5, this minus log ab is minus, yes. Minus log ab is minus log 0.46, a positive fraction only. So decreasing from here to here, decreasing. So xb by xa is positive, but this log, what is this term is actually, see, term is minus log ab is decreasing. So net result is negative. So this is a negative. Where I have written this is a negative area, is a negative quantity. So okay, fine, it is a negative quantity. Now I will move from this point. Okay, the negative quantity. I tell you one thing, you expected this to be a negative quantity. The thermodynamic knowledge says it should be a negative quantity. Why? What is the activity? In a solution, AB less than 1. Log of less than 1 is what? Negative. Makes sense. Okay. So let us write down these few points. I'm removing this. Okay. These are not required. I'm removing this. Okay. Achha, here let us write down a few lines. Okay. So it's okay. So let us start here. From here. From here also I'm giving you, or A is what? Log A is negative quantity, or A is what? Antilog of a negative quantity, A is antilog of a negative quantity. Okay, antilog of the negative quantity, or the negative quantity, the negative quantity. Okay, is what? Antilog of a negative quantity is what? Is a fraction. Log of a fraction is negative, so antilog of a negative is a fraction, which is a fraction which is less than 1, and that makes sense. Activity that you have to determine right here. Activity at where? This don't forget. This is your question. This is your problem. Find activity without doing any experiment of A. For B it was given. Okay. So this part is over. Okay. So let us write down a few lines here. So remove all this. Remove all this. Now few comments. This is also over. This is over. You have understood, I guess. I'll remove this. This makes sense. Okay, this retain the figure. This it makes sense. It makes sense. It makes sense. Or it is this. It makes sense that a is a less than 1. It makes sense. Uh, it makes sense as a in a solution. In a solution must be less than 1. So we are satisfied. Our integration of Gibbs-Duhem equation is over. We have determined activity of A. No problem. Okay. So quantitatively we cannot give because then we have to measure area under the curve. You see, actually, there are several. What is this called? You have actually small squares or big squares. Okay. See, actually, 1 unit is how much, and 1 unit is how much in the y direction and x direction, and get the area. So and see how many squares are there. Such squares are there. So get the area under the curve. Okay. Very good. So this is actually this one. So now note. Now few notings is important. One by one. Note the xp by xa versus minus log ab plot curve on its either end on its either end on its either end. Okay, its curve on its either end is is asymptotic in nature. Asymptotic in nature. That is, for example, both sides. Here, when it is 0, this goes to, when this is 0, other goes to infinity, asymptotic. When y-axis is 0, x-axis goes to infinity, asymptotic. Means it will never be infinity. It is closing towards infinity. And all the time, that is decreasing the difference. Decreasing the difference, but never becomes infinity. So this is the asymptotic nature. So nature, that is, for example, here I am giving, that is for what is this called? That is okay. That is for example. That is for example. Let us write a little faster. When xb by x is 0, as I told you, this is relevant to our discussion. That's why I have taken up this one. I am considering this one, this side, because this side is important, not this side. So this example I am taking. When xb by x is 0, minus log ab becomes infinity, becomes plus infinity, becomes infinity. Yeah. Thus the curve, thus the curve tails up, tails up, you know, tails up, becoming gradually narrow, narrow and narrower, narrower, more further narrower, further narrower, still narrower, still narrow, still narrow. So this tails up. Okay. So tails up as xp by xa tends to 0, tends to 0. It is necessary. It is necessary to cut off to cut off, it is necessary to cut off the tail.
1 hour 40 minutes.
Okay, another 10 minutes or 15 minutes. Cut off 10 to 15. 15. Cut off the tail. Necessary to cut off the tail as shown in figure 1. As shown in figure 1. I am cutting off the tail. I am cutting off the tail. I have not shown yet. So it is possible. How will you ever measure? It goes to infinity. So you have to cut off at some point, admitting a little error, negligible error. So I am cutting off. Just I am drawing this little bigger. This is the cutting off plane. So from here, I am drawing this little, this and this area, between this area under the curve and covering x-axis. Good, very good. So it is necessary to cut off the tail as shown in figure 1. Oh, I have not mentioned this is figure 1. Please, this is figure 1. I am very sorry. This is figure 1 I mentioned, but I forgot. Figure 1. The resulting plot in figure 1. Please include this. What is this? It is necessary to cut off the tail as shown in figure 1 to make the area measurement at any value. While I will cut off at any value close to, at any value of xb by xa close to 0. To make the area measurement feasible. So the error incurred is negligible. For this approximation is negligible. Okay, this is the answer. Okay, so this, follow these 2 points. Okay, next, okay, a few more points. Okay, also note where I shall write. I can remove this easily. This is all over. Also note here, I don't know which star, 3 star. Negligible. Give 3 star. Also note when the A corresponding to x is x is 0.666 is known. Another thing you can determine also. Activity was asked at this composition, what is the activity of A? But you can determine another thing also. What another thing? Activity coefficient. Activity known and mole fraction known. So activity coefficient. Not only that, many thermodynamic properties can be found, can be obtained. What is this? Suppose activity is known, then you can get what? Partial molar free energy. GA bar M is what? R T ln activity of A. You know the activity of A. T is the temperature must be given. R value you know. Partial molar free energy of mixing for A. What else? Suppose you know the gamma, as I will discuss now. Activity coefficient you can determine. The activity coefficient you can also determine. So also using this, knowing activity coefficient, what thermodynamic property you can determine, you can find at the same time partial molar excess free energy. So GA bar excess, what is that? R T ln gamma A. So since gamma A you will find now, so gamma A. So many things can be found, you will know. So let us start. Also note that the activity corresponding to excess is known. The activity coefficient is known. The activity coefficient gamma A. The activity coefficient gamma A, which is nothing but A by XA, both of which you know is for the same composition. Composition dependent. Activity is composition dependent. Gamma is composition dependent. Okay. So for the same, also temperature dependent gamma. Okay. For the same composition, this I have said. Okay. Temperature, pressure, and composition. Okay. And so is activity. So what is this? For the same composition means 0.666 of XA. For the same composition can be found out. You can write. We can also find out the following thermodynamic properties. Thermodynamic properties. Thermodynamic properties. What is this? I am giving you. What is this? Tell me. GA bar M. Partial molar free energy of M. What is this? Is nothing but R T ln activity of A. And which you have measured activity of A at that composition. Obviously composition dependent. So for this composition GA bar M. And similarly, what is? And GA bar excess. What is that? RT ln gamma A. So on and so forth. Okay. So still another point. These are all over. So next point is the usefulness. Next, the usefulness of the Gibbs-Duhem equation, of the Gibbs-Duhem integration, of the Gibbs-Duhem integration, Gibbs-Duhem integration is that we don't have to. What I have already said. I have already said that we don't have to. We don't have to. Is that we don't have to carry out separate experiment. To carry out separate experiment to find the A, to find the activity of A for any given composition at any given composition given composition at when the AB when the AB is experimentally determined. determined as a function of composition. So this I said already, that you experimentally find out activity of B for different compositions, and for A you don't have to. You can think that similarly we have to carry out for A to find the activity of A. No, you don't have to. Gibbs-Duhem equation, integration of Gibbs-Duhem equation will help you. Okay, this is the message, the usefulness of this. Okay, because this last point is what? If we want to next, since I said there is a little error, since cutting off, you are eliminating this part, discarding this part, ignoring this part, this part, negligible. But if you want to be perfect, 100% perfect, want to be precise, fully precise, okay, or say meticulous, then this is the method. There is no error, but follow this. This last thing. If we want to eliminate the error, however little, in the above method, in the above method, in the above method, we have to resort to resort to the Gibbs-Duhem equation, to the Gibbs-Duhem equation, Gibbs-Duhem equation, what is a Gibbs-Duhem equation? Written in terms of the activity coefficients. In terms of activity coefficient, gamma, which is tell me 2 I gave you Excel similar. This X A DLN A, that will be X A DLN gamma A plus XB DLN gamma B is 0. This is the Gibbs-Duhem integration of this you have to do. Then why you will not have any error? Why? What is the magic? This X A DLN is 0. Unlike in the previous case, right? Unlike in the previous case, unlike in the previous case, in which
1 hour
4 minutes, in which AB is 0, unlike in the previous case, in which AB is 0 when XB is 0. This we had. These results actually, these things. XB is 0, making minus log AB is plus infinity. This infinity comes into this infinity we get, okay, and we had to cut off the tail. We had this difficulty to take into account the entire area because it goes to infinity, plus infinity. Unlike in this previous case, the gamma B is not 0. when gamma b is not 0 at xb is 0. At xb is 0, ab is 0. But gamma b is, you have to actually, if you do this integration in the same way we have done, it will be minus log gamma b, but gamma b is not 0. So there is no question of any infinity. There is no any question of having infinity, place infinity. So why sir? The gamma b is not 0 at xb is 0. What it is then? But is gamma b 0. Remember, at xb is 0, gamma b, Henry's law, activity coefficient. In the dilute region, gamma b is gamma b 0. Linear part, gamma b is gamma b 0. But is gamma Henryan activity coefficient at 0 concentration of B. That's why this 0. That's why this 0. 0 concentration of B. That is 0 concentration of B. That is xb is 0, which is called actually infinite. Another term is there, infinite dilution. Independent dilution activity coefficient gamma b 0. Actually, I say it is gamma b at xb is 0. So gamma easy, gamma b 0. So this is Henryan activity coefficient at xb is 0, or Henryan activity coefficient. I would say rather Henryan activity coefficient. Okay, very good. At 0 concentration, Henryan activity coefficient at 0 concentration of B. xb is 0, infinite dilution, which is a non-zero quantity. Which is a, unlike it is not 0, AB is 0, but gamma B 0 is not 0, which is a non-zero quantity. So, which is non-zero quantity, and minus log gamma B, and minus log gamma B, log minus log gamma B, yes sir, minus log gamma B, and minus log gamma B will not be infinity, will not be plus infinity, but a finite quantity, but a finite quantity. But a finite quantity. Following the preceding procedure is this, but with respect to gamma activity, in terms of gamma you proceed, rather than in terms of activity, in terms of gamma you proceed. The same procedure following the preceding procedure following the preceding procedure, gamma A, this gamma A at any given composition, at any given composition can be fully correctly determined. Hence, also, one second. Hence also the activity. When you determine gamma activity coefficient at any composition, you can determine activity also. because also the, and hence also the activity of A, which is nothing but is gamma A Xa. So gamma is known and Xa is known, so both are known. So with this, we have completed integration of Gibbs-Duhem equation for binary system. Thank you. Next day, we'll consider regular solution or thermodynamic model. Thank you very much for your patience and for your interest and for your dedication. Thank you once more, and okay, see you in the next class. Bye.